This is the radian measure tutorial. Radian measures relate directly to angles and degrees, so we're going to begin this tutorial by discussing the central angle. A central angle is any angle whose vertex lies at the center of a circle. So if you had a circle here, the central angle that I'd be referring to in this circle is this angle indicated by the arrow going around. Now imagine that this circle were sitting on your typical coordinate plane graph. So there were an x-axis and a y-axis traveling through this circle. You could look at this and say that this circle must have a central angle measure of 270 degrees because we're traveling counterclockwise and we go through all three coordinates here, coordinate 1, 2, and 3. Now an important aspect of circles and central angles is arcs, and they're intercepted arcs. An intercepted arc is the portion of the circle's arc that is within the boundary of the endpoints of the sides of the central angle. So if our central angle, if you recall, had these two sides to it, here and here, then the portion of the circle's arc that's within the boundary of those endpoints of the sides of the central angle is this green portion of the arc right here. That's all inside of this angle right here. We say it's inside because this is the angle that we're referring to. We're not referring to this information out here, that 90 degrees that we've left out. We're referring to that 270 degrees all the way around inside the circle here. Now the radian is the measure of the central angle when the radius of the circle is equal to the length of the intercepted arc. So now remember, when you're dealing with a unit circle, that's a circle whose center is at the origin of a coordinate plane and whose radius is 1. So also remember that the circumference of any unit circle is simply 2 pi, because circumference is equal to 2 times pi times the radius. And if your radius is 1, then your circumference is simply equal to 2 pi. So if you were to travel from that origin all the way around the distance of the circle, you'd end up with a value of 2 pi. That's the distance in radians around the circle. So I'll teach you right now the formula to convert from degrees to radians and vice versa from radians to degrees so that you can see this a little bit more clearly. When converting from radians to degrees, we multiply radians by 180 degrees over pi radians. And when converting from degrees to radians, we multiply degrees by pi radians over 180 degrees. So let's do a couple practice problems. Let's convert the following measures to radians. So we'll start with that 240 degree measure. We have 240 degrees, and we want to convert that to radians. So we're going to use this conversion right here. We're going to multiply the degrees by pi radians over 180 degrees. So multiply by pi over 180 degrees. And what you'll get is 240 pi over 180. We can cancel out the zeros, and then 24 over 18 reduces to 4 over 3. And that pi is still on top in the numerator. So when we convert 240 degrees to radians, what we have is 4 pi over 3 radians. That's the radian measure. Now let's convert negative 45 degrees to radians. So we'll have negative 45 degrees, and we're going to multiply by pi over 180 degrees. So we're going to get negative 45 pi over 180. Negative 45 over 180 reduces to negative 1 over 4, and that pi stays on the top. So we have negative 1 pi over 4 radians when we convert negative 45 degrees to radians. Now let's go the opposite direction. Let's go from radians to degrees. So convert the following measures to degrees, and we're going to use this top formula when we go from radians to degrees. It's just the reciprocal of the bottom formula. We're going to be multiplying now by 180 over pi. So for this first problem, we have 4 pi over 3 radians times 180 degrees over pi. So 4 times 180 is 720. And we have our pi there. And the bottom, 3 times pi, is 3 pi. Now our pi's are going to cancel, and we're going to be left with 720 divided by 3, which is just 240 degrees. So 4 pi over 3 radians is equal to 240 degrees. Now let's deal with 3.25 pi. So we have 3.25 pi times 180 divided by pi. Well, 3.25 times 180 is 585. So we have 585 pi on top divided by pi on the bottom. So our pi's are going to cancel, and 3.25 pi is equal to 585 degrees. Now that we've done a little work converting degrees to radians and radians to degrees, let's do a little work on arc lengths. To calculate the value, or the distance, of an intercepted arc length, we use s, which stands for the length of the arc, and set that equal to the radius times theta. So the radius of the circle that we're dealing with times theta, that angle and standard position of that circle. So it'll be easiest if we just work through a couple problems with that formula. Find the length of the indicated arc measures to the nearest tenth. Let's start with the circle on the left. We're calculating the arc length, s. And s is equal to the radius, so the radius of this circle is 16 feet. So 16 times theta. And theta in radians is 3 pi over 2. Now, when dealing with calculating the length of the intercepted arc, you always want to keep your measure theta in radians, not degrees. So, let's multiply 16 by 3 pi over 2. So s, our intercepted arc length, is 48 pi over 2. We'll divide by 2, and s has a value of 24 pi feet. That would be the length of that bold arc along the outside edge of the circle. Now let's take a look at the circle on the right. Again, s, the intercepted arc length, is equal to the radius of the circle, in this case 13 feet, times theta. In this case, theta has been given to us as 270 degrees. Now we want to convert that into radians. So I'm going to multiply that by pi radians over 180 degrees. When you do that, we get 270 pi over 180. We can cancel out those zeros, and we have 27 over 18, which is just 3 over 2. So we're dealing with 3 pi over 2 radians. That's our theta in radians. So I'm going to write that here, 3 pi over 2. So we want to multiply 13 by 3 pi over 2 to find our intercepted arc length. So s is equal to 39 pi over 2. I don't want to make a decimal answer, so I'm going to leave my answer as 39 pi over 2, and that's feet that we're referring to here. That's the arc length of this bold arc right here that travels around that central angle. Now let's go ahead and move on to another problem. Which quadrant does the terminal side of this angle lie? And the angle we're referring to has a value of negative 3 pi over 4 radians. Well, the easiest thing to do here would just be to convert that radian measure into degrees. So we have negative 3 pi over 4 radians, and we want to multiply that by 180 degrees over pi radians. So when we multiply negative 3 times 180 degrees, we get a value of negative 540. And that pi is still on top, so negative 540 pi over 4 times pi on the denominator, so 4 pi here. Now our pi's are going to cross cancel, and we have negative 540 degrees divided by 4, which is negative 135 degrees. So remember to start on our x-axis, and we want to travel counterclockwise because it's negative. So I'll draw in our measure here. Negative 135 degrees, if this is 90, we go 45 degrees past that 90 in the negative direction here, and we get a total of negative 135 degrees. So remember, when you're given problems like that, if they give you a radian measure, it's easiest to just convert that into a degree measure and then draw your angle in standard position. So the answer to this question then is this angle lies in quadrant 3, because remember, that's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now let's take a look at one more problem. It's pretty common when dealing with radian measures to start dealing with problems like Ferris wheels and bicycles and calculating arc lengths and travel distance around these different wheels. So I'm going to give you a word problem about a Ferris wheel. The radius of a particular Ferris wheel is 25 meters. Solve for the number of radians through which one of the carriages on the Ferris wheel travels when the carriage moves forward a distance of 32 meters. Now, when you get into complex problems in pre-calc, geometry, physics, it's easiest to draw an image of what's going on. Draw yourself a figure. So I'm going to go ahead and draw in the figure of a Ferris wheel here. Now they said that this particular Ferris wheel has a radius of 25 meters. So I'll go ahead and highlight that in here, 25 meter radius. And what they'd like us to do is solve for the number of radians through which one of the carriages on the Ferris wheel travels when the carriage moves forward a distance of 32 meters. Well, let's deal with this carriage right here. Because if I drew out from the center of this circle, he'd kind of be right there on the x-axis. And I want to go forward 32 meters, so I want to go around in this circle a distance of 32 meters. Now remember our formula. S, that's the intercepted arc length, is equal to the radius of our circle times theta. Well, the arc length that we've traveled is 32 meters. So I'll write that over here for S. And the radius of our circle is 25 meters. Now we want to solve for theta. That's the number of radians through which one of the carriages of the Ferris wheel is going to travel when we move forward that distance 32 meters. So I'll write theta in there. So to solve for theta, I'm just going to divide by 25 on both sides here. And when you do that, we get a value of 1.28 radians. That's our value of theta here. So I'll just put in theta right here on our circle. Now it's possible to make these problems a little bit more complex, but usually the way that they do that is by having you draw a more difficult figure. So remember to always draw the figure on these word problems if you're having difficulty getting started. It'll really help you visualize exactly what it is you're calculating. What makes it difficult for people is when they try to not draw these diagrams and get through it. And textbook publishers and people who are creating problems, teachers for exams and things like that, they're not doing it to be evil. They're doing it because they want to add a level of difficulty to the problem, and they're counting on people not drawing things out and working through them. So use that to your advantage and draw these figures out when you're having difficulty. Alright, so the next topic I'd like to discuss is degrees, minutes, and seconds. Now, the degree is a unit of measure that is equal to 1/180th of a straight angle. And we can use that for different calculations. So let me show you how this works. I'm going to ask you to convert 56 degrees, 13 minutes, and 25 seconds to degrees, and I'll show you how it's done. For these problems, it's easiest if you consider degrees to be hours. Now, this is the symbol for minutes here, and this is the symbol for seconds. So, if we're converting it to degrees, we know that we already have 56 whole degrees. So, I'm going to start with that. We have 56 degrees. And then we'll move on to our minutes. We have 13 minutes. Now, if we're considering degrees to be hours, and we want to convert everything into degrees, we want to convert our minutes into hours as well. So we want to take our minutes and we want to divide them by the number of minutes in an hour, which is 60 minutes. Then we also want to factor in our seconds. And again, we're trying to get to degrees, and we want to consider degrees to be hours. So I'm going to take our seconds and I'm going to divide them by the total number of seconds that are in 1 hour. And there are 3,600 seconds in 1 hour. So now you want to put this directly into your calculator as you see it. 56 degrees plus 13 over 60 plus 25 over 3,600. Don't worry about putting in degrees into your calculator. When you do that, you get an answer of 56.224 degrees. Now with these problems, when you're given degrees like this in minutes and seconds, your minutes and seconds are never going to get you over the number of degrees that you have. So you're never going to go from 56 all the way up to 57 degrees, let's say, because every degree is an hour, and you only have 13 minutes and 25 seconds. You'll also never see something like 62 minutes, because you might as well just say 1 hour and 2 minutes. And you're never going to see something like 3,700 seconds, because there's 3,600 seconds in an hour, so in that case you just have 1 hour and 100 extra seconds, and you would bump your degree up by 1 to account for that. Now, degrees, minutes, and seconds are usually used in nautical units and in aeronautics as well. So ship captains or pilots might be using degrees, minutes, and seconds as opposed to just degrees. It gives you an extremely fine angle measure when you start to use minutes and seconds, and you can become more accurate than just degrees. Now let's take a look at a problem that asks us to go the opposite direction. So in this problem, they're giving us degrees, and they'd like us to convert it to degrees, minutes, and seconds, and that's often abbreviated as DMS. So what you want to do in this case is take a look at the whole number of degrees that you have already. We already have a full 26 degrees. So I'm going to write that over here off to the left. What we're concerned with is getting this 0.48 into minutes and seconds. So what we'll start with is that 0.48. I'm going to take the 0.48 and I'm going to multiply that by the number of minutes in 1 hour. So 60 minutes for every 1 hour. And remember that an hour is essentially a degree in this kind of unit. So we had 0.48 degrees, and we're multiplying it by 60 minutes over 1 degree. So our units are going to cross cancel here. We're going to get out of degrees because they're on top and bottom. And we're going to end up in only minutes. When you multiply 0.48 times 60, you end up getting 28.8, and our answer is in minutes. So I'm going to take that whole number of minutes here, that 28, and I'm going to write that right here. We were given 26 degrees, and we have 28 minutes. Now I want to take the decimal portion of our minutes here, so that 0.8 minutes, and I want to multiply it by the number of seconds that are in 1 minute. When we do that, our minutes are going to cancel because they're on top and bottom, and we're going to end up in seconds. So 0.8 times 60 seconds is going to give us 48. And our answer is going to be in seconds. So now we can write that over here, 48 seconds. So when you convert 26.48 degrees to degrees, minutes, and seconds, you get 26 degrees, 28 minutes, and 48 seconds. Now the last thing I'm going to teach you in this tutorial is how to calculate the area of a sector of a circle. So in this problem, they'd like us to determine the area of the arc and round to the nearest 100th. Now they haven't actually given us a circle with an arc in here, so you can either draw that circle or imagine it. I'll draw that circle in here for you. So let's imagine that this is our circle, and we're given a radius of 14 feet and a theta, so an angle measure of 19 pi over 12. And if you work that out, that's roughly 3/4 of the circle. So I'll draw another angle down here. And what we're doing is calculating the area of this sector right here, because our angle measure, theta, is 19 pi over 12. Alright, so we'll just use our formula, which is area is equal to 1/2 the radius, which is 14, squared, times theta, which is 19 pi, over 12. So we'll continue on our work here. 1/2 of 14 squared, which is 196, times 19 pi over 12. And you can put it directly into your calculator like that. When you do, you get an answer of 2,924.82 square feet. Alright, so now let's take a look at a problem in which they do give you a drawing to work with. So in this problem, they'd like us to determine the area of the sector and round to the nearest hundredth. And again, the sector that we're looking for is here. I've marked it in green. So let's use the information that they gave us. Area is equal to 1/2 the radius, which in our case is 4 centimeters, squared, times theta, the distance around that we've traveled for that particular sector. And in this case, that's 3 pi over 2 units. So area is equal to 1/2 of 4 squared, which is 16, times 3 pi over 2. And when you work all that out in your calculator, you get 37.7 centimeters squared for an answer.